Welcome viewers to the second segment of the fifth lecture for the online series of lectures for the course of linear algebra. In the previous segment, we learned the definition of a vector space. We saw some examples of vector spaces as well. In this segment, we will start with the definition of a vector subspace. Let V be a vector space over the field F. A subspace of V is a subset W of V which is itself a vector space over F with the operation of vector addition and scalar multiplication on V. Okay, so we are given this subset W of V that needs to be a vector space with respect to the same vector addition and scalar multiplication of the vector space V. Okay, now a direct check of the axioms of the vector space reveals that the subset W of V is a subspace if for each U and V in the vector space in W, the subset of V, the vector U plus V is also in W. That's the first thing, is the closure of vector addition. The zero vector is in W. Okay, so the subset that we started with, that requires to be closed under vector addition. That's what it means, by the fact that U and V being in W, U plus V also has to be in W. The zero vector has to be in W. For each U in W, its additive inverse, negative U, has to be in W. Okay. For each U in W, and each scalar C, the vector C times U has to be in W. Okay, these are the things which need to be checked to prove that W is a vector subspace of the given vector space V. Okay, so the other requirements, for example, the commutativity and associativity of vector addition and the properties listed in 4a to 4d related to scalar multiplication are automatically fulfilled, as these properties are related to the two operations, vector addition and scalar multiplication, right? Because W is equipped with the same operations, vector addition and scalar multiplication, we don't need to check those properties explicitly. All right, they are automatically fulfilled. Okay, so these things need to be checked. The closure of vector addition, which we write here, the presence of the zero vector in the subset W, and for each vector in W the additive inverse has to be in W as well, and for each vector in W and each scalar C, the scalar multiplication of that scalar with this vector U has to be in W as well. Okay, if we check these things, then and if these four things are satisfied, we say that the subset W is indeed a vector subspace of the given vector space V. Okay, one actually needs to check even less to see if it's a subset, if W is a subset of a given vector space, as given by the following theorem. Let me put the result in terms of our first theorem, theorem 1. As it turns out that we don't need to check all these four properties to ensure that a given subset is a vector subspace. Okay, a non-empty subset W of V is a subspace of V if and only if for each pair of vectors UV in W and each scalar C in F, the vector CU plus V is again in W. Okay, proof. Suppose W is a non-empty subset of the vector space V such that C times U plus V is in W for all UV in W and for all C belonging to the field. Okay, suppose that this holds. We need to check that W is a subspace of V. Okay, since W is non-empty, there is a vector which we denote by W in big W, which is the subset of V. Okay, and we know that this holds, right? Since this holds, we must have -1 times this vector W plus W which is equal to the 0 vector, right? Because W is an element in the vector space V, and the the objects in the vector space V should satisfy all the properties listed in the definition of a vector space, and hence the additive inverse of W being minus W, should result in the 0 vector when it gets added to the vector W, right? And we know that C times U plus V is in W. So -1 times W plus W, which is the 0 vector according to the vector space definition, also belongs to W. So we just check that the 0 vector is in the subset W. Given any vector U in W and any scalar C in the field F, again, since this holds, C U plus the 0 vector, okay, should be in W as well. But C times U plus the 0 vector, according to the definition of a vector space, because they belong to the vector space V, so the addition of these two guys will be equal to C times U, and according to the hypothesis, this has to be in W. Okay, which means that W is closed under scalar multiplication. All right. So, well, it means that for any scalar C in the ground field F and for any vector U in W, C times U is also in W. In particular, -1 times U which is equal to minus u, a simple fact that had been checked earlier using the definition of a vector space, is also in W. Okay, since cu is in W, and we just take the scalar c to be minus 1. All right, so given each vector in W, its additive inverse is also in W. Okay, all right. Finally, closure of vector addition for u and v in the set W. According to this hypothesis, I choose C to be the scalar 1. Okay, 1 times u plus v is in W, right? Which means that 1 times u, according to one of the properties of the vector space, which is 4a, which is listed under 4a, is just u. Okay, so u plus v is again in W, which means that W is closed under vector addition. It means that, so we checked all the 4 properties that we discussed earlier, and hence W is a vector subspace. Thus, W is a subspace of V. Okay, so this is one direction. Conversely, if W is a subspace of V, that is, if W is a subset of V that is a vector space over F by its own right. Vector space over F then for UV in W and C in the field of scalars, by property 4, Cu is in W. And since Cu is in W and V is also in W, by property 3, property 4 is the closure of scalar multiplication, and property 3 is the closure under vector addition. So property 3 of vector space tells us that Cu plus V will also be in W. And by property 3, Cu plus V is in W. Okay, QED. Okay, now it's time to look at our fifth example. There are several examples under example 5. If V is a vector space, V is its own subspace. Okay, it is trivially a subspace of itself. The subset of V consisting of the zero vector only is also a subspace of V, called the zero subspace of V. One can easily check that the subset of V consisting of the zero vector alone is a subspace of V called the zero subspace of V. Okay, so this gives us two trivial subspaces of a given vector space. Then we have another example under example 5. In F to the n, remember that given a field F, we can construct the space of all n tuples called F to the n, where each component of the n tuple takes value in the field F, and we have seen that it forms a vector space F over the ground field F. So in F to the n, the set of n tuples, I should write the subset of n tuples x1, x2 all the way up to xn, with x1 is equal to 0, is a subspace. Okay, so you can immediately verify that it's indeed a subspace by using theorem 1. Okay, however, the set of or the subset of n tuples x1, x2 all the way up to xn, with x1 is equal to 1 plus x2 is not a subspace. Okay, for n greater than or equal to 2. So you should be able to verify that at least one of the properties of vector space is not going to be satisfied if you choose this subset, if you take this subset, right? So you see that, in particular, you can check that the closure of vector addition is not fulfilled if you choose x1 to be equal to 1 plus x2. Okay, so suppose that you take, so if x1 is equal to 1 plus x2, then the n tuple reads 1 plus x2, x2 all the way up to xn, and you add it to another n tuple belonging to the same subset, 1 plus x2 prime, x2 prime, x3 prime, this is x3 dot 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 xn, so x3 prime, xn prime, and when you add them according to the rule of addition here in this vector space, it's 2 plus x2 plus x2 prime. Okay, then x2 plus x2 prime, x3 plus x3 prime, finally xn plus xn prime. So you can never write this guy as 1 plus this thing, right? So 2 plus x2 plus x2 prime is not equal to 1 plus x2 plus x2 prime, and hence the subset that we are considering is not closed under vector addition, is not closed under vector addition, and hence is not a vector subspace. Okay, good. Now the next example is related to matrices. An n times n matrix over the field F is called a symmetric matrix. Symmetric matrix if Aij is equal to Aj for all ij in this finite set 1, 2 all the way up to n. Okay, the subset of all symmetric matrices over F forms a subspace of the vector space F to the n cross n. Okay, which we know that this is the vector space of all n times n matrices over the field F. Okay, so you need to verify that it's indeed a subspace, the subset of all symmetric matrices over F, which is an easy exercise. Okay, now the fourth example is again related to matrices. An n times n matrix A over the field C of complex numbers is Hermitian if Ajk is equal to the complex conjugation of AKJ. The right side is the transposed conjugate. Okay, you first take the transpose of the matrix by exchanging, by interchanging the rows with the column, and then take the complex conjugate of each entry. That way what you get is called, the is the Hermitian is the transposed conjugate of the given matrix, and if that's the same as the original matrix, then it's called Hermitian. Okay, and this has to hold, in other words, for all kj in this finite set 1 to n. Okay, so one can check that 2 times 2 matrix is Hermitian if and only if it has the following form. So this is z, this is x plus iy, this is x minus iy, this is z again, this is not z in general, this is w, where x, y, z and w are real numbers, where x, y, z, w are reals. Okay, so it just follows from the definition, so take a complex 2 times 2 matrix. Okay, you don't need to take this to be a real, so take 4 different complex numbers here in the form of a plus ib, and then apply this definition, and you will arrive at this form. Okay, so I require you to check that this is indeed true, that a 2 times 2 complex Hermitian matrix has this form. Okay, all right, so now one immediately sees that this vector space C to the n cross n which is the vector space of all n times n complex matrices. Okay, right, it's a special case of this vector space F to the n cross n. We just choose we just take the field to be the field of complex numbers. Okay, so it's the vector space of all n times n matrices over the field of complex numbers. Okay, so now the subset, we take a subset from this vector space, which is the subset of all n times n Hermitian matrices. Okay, now I claim that the subset of all n times n Hermitian matrices here is not a vector subspace. Okay, the subset of all n times n Hermitian matrices in C to the n cross n does not form a vector subspace. Why? So remember that this vector space is defined over the ground field C. That's the the scalars take their values from this set, from this field to be more specific. Okay, so now if okay, so if you take n times n Hermitian matrices, you'll see that all the diagonal entries of such matrices are real. Okay, so let me write it here. The diagonal entries here are all real. So remember, so let me write down the definition of an Hermitian matrix. It was like this, right? AJK is supposed to be equal to the transposed conjugate, right? When I take the transpose, then AJK becomes AKJ, and I take the complex conjugate, okay? And that has to be the same as AJK. That's the definition of a Hermitian matrix. Okay, and so if I just take J to be equal to K, then it reduces to AJJ being equal to the complex conjugate of AJJ. What does that mean? It means that all the AJJs should be real numbers. Okay, that's why all the diagonal entries of a Hermitian n times n matrix have to be real numbers. Okay, what happens with so when I take the n times n Hermitian matrices as a subset of this vector space C to the n cross n, then the scalars are taking values from this field C. So I take the scalar I and multiply it with the Hermitian matrix A. All right. And what are the diagonal entries of this matrix? The diagonal entries are IA11, IA22, all the way up to IANN. Okay? And these guys are not in general real numbers. Okay, they are not in general real numbers. So what does it mean? If they are not real, they cannot if these diagonal entries are not real, it means that I times A can never be a Hermitian. Okay, so we have seen that although A is a Hermitian matrix, the scalar I times A is not a Hermitian matrix, meaning that the subset n times n, the subset of all n times n Hermitian matrices, okay, the subset of C to the n cross n, okay, this subset is not closed under scalar multiplication, so it's not a vector subspace of C to the n cross n. Okay, so let me write the conclusion. We therefore see that the subset of all n times n Hermitian matrices is not a vector subspace of C to the n cross n. Okay, all right. I leave it as an exercise for you to check that the set of all n times n complex Hermitian matrices is indeed a vector space over the field of real numbers. It is important. I change the ground field now. It's no longer C, it's the field of real numbers. Okay, with the usual operations of vector addition and scalar multiplication. Okay, this is an exercise for you. Okay, now our sixth example is again related to a homogeneous system of linear equations. Example 6. The solution space of a system of homogeneous linear equations okay, so this is our sixth example. So let A be a matrix of size m times n over the field F. Okay, the set of all n times 1 matrices X over F satisfying A times X is equal to 0. Okay, so you see that A is an m times n matrix, and that is getting multiplied with an n times 1 matrix X to result in an m times 1 matrix. So this is an m times 1 zero matrix, okay, with all the entries being zero here. So this is a homogeneous system of linear equations. This is a subspace all such matrices satisfying this equation is a subspace of f to the n cross 1. Okay, f to the n cross 1 is the set of all n times 1 matrices over f. Okay, and I'm just taking all those n cross 1 matrices over f that satisfy this equation, and that those matrices constitute a set, and that set is going to be a subspace here, subspace of this vector space. Okay, so this is the vector space of all n times 1 matrices over f. Okay, so whenever I'm given a subset of a given vector space, and I need to check that if it's actually a subspace of the given vector space, I have to apply theorem 1. Okay, so let us apply theorem 1 in this case as well. One must show that if AX is equal to 0 and AY is equal to 0 and C is any scalar, then A times A of A of or A acting on Cx plus Y is also 0. This is what we need to show, right? So A acting on X results in the M times 1 0 matrix, and A acting on Y also results in M times 1 0 matrix. For notational convenience, I have just written 0 here, but it means that we have an M times 1 0 matrix on the right side. Okay, and if this holds, if these two things hold separately, then A acting on Cx plus Y is again the M times 1 0 matrix, and this is a consequence of a more general fact proven below. So let me state the lemma first and then I'll prove it. Lemma 1. If A is an M times M matrix over the field F, and B, C are N times P matrices over F, then A times alpha B plus C is equal to alpha A times B plus A times C for all alpha in the field. So the proof is straightforward. So I take the ijth entry of the matrix on the left side, A times alpha B plus C ij. Okay, now by the definition of matrix multiplication, we know that this is equal to aik alpha b plus c kj, all right, where k runs from 1 to n. All right, and since alpha is a scalar, we can write it as alpha times the sum over k aik bkj plus sum over aik ckj. Okay, and that means, again, using the definition of matrix multiplication, we write it as alpha abij and this guy as acij, right? And this is nothing but alpha times ab plus ac, the ijth component of this matrix, which is the right side, which is the ijth component of the matrix on the right side here. Okay, QED. All right. So going back to our example 6, we saw that ax is equal to 0 holds and ay is equal to 0 holds, and c is a scalar. A times cx plus y, according to this lemma, can be written as, sorry, this c is a small c, this is c, small c, which is a scalar, right? And this, according to this lemma, can be written as a c times ax plus ay, right? And since they are 0, this is 0. Okay, good. Now we have a theorem, an important theorem. So let me state the theorem and then I'll prove it. It's Theorem 2. Let V be a vector space over the field F the intersection of any collection of subspaces of V is a subspace of V. Okay, proof. Let WA, where A runs in some index set, okay, be a collection of subspaces of V and W equal to the intersection of all these subspaces, and W be their intersection. Okay, then we know from elementary set theory elementary set theory that W is the collection of all elements belonging to every WA. Okay, so here W is the collection of all the elements that belong to every WA here in the intersection. Okay, all right, let U and V be two such elements of the intersection, and C is a scalar. By definition of W, U and V belong to each WA, and V belong to each WA. Okay, and since WA is a subspace of V, C times U plus V also belongs to each WA. That's right. Is that right? Right. So we have come to the conclusion that CU plus V belongs to each WA. Thus, since CU plus V belongs to each WA and W is the intersection of all WAs, CU plus V must belong to W. Okay, so we started with U and V belonging to W, and C is any scalar, and we prove that CU plus V is also in W. What does that mean? By Theorem 1, it tells us that W is a subspace of the vector space V, QED. Okay, now a remark to this Theorem 2. Let me erase everything and then write down the remark. From Theorem 2, it follows that if S is any collection of vectors in V, not necessarily a subspace, is any collection of vectors in V, then there is a smallest subspace of V which contains this set S. which contains S. That is a subspace Now I'm giving the definition what it means by a smallest subspace. Okay, that is a subspace which contains S and which is contained in every other subspace containing S. In every other subspace containing S. Okay, so let me explain. S is a set, okay, of a given vector space, something like this. Okay, S is just a subset. It's not a subspace in general. Okay, it's just a collection of vectors of the given vector space V. Okay, now there are many subspaces that contain S, like this one. This is a subspace. Say this is again a subspace that contains S. Okay, then this is a subspace that contains S. Okay, so the point is that there is a smallest subspace that contains this subset S. Okay, by smallest it means that if the subspace that is claimed to be the smallest subspace that contains S, then all other subspaces that contain S has to contain this smallest subspace. That's the whole point. Okay, it is so in this picture W is the smallest subspace. So the situation is not like this picture. It's just a schematic diagram in order to explain what's happening. Okay, so W, if in this picture you see that all these subspaces contain S, okay, of which W is the smallest, which means that W is contained in all the subspaces containing S. Okay, that's what I have written down here. All right, now using this remark, we have a definition of a span. Let S be a set of vectors. Let S be a set of vectors in a vector space V over F. The subspace spanned by S is defined to be the intersection W of all subspaces of V which contain S. In Theorem 2, we have seen that the intersection of subspaces of a given vector space is also a subspace. Okay, and the intersection of all subspaces that contain S has a name, which is called the subspace spanned by the set S. Okay, which contain S. When S is a finite set of vectors, S is equal to is a finite collection of vectors u1, u2 all the way up to un, say, we shall simply call W the subspace spanned by the vectors u1, u2 all the way up to un. Okay, so this is the definition of a vector subspace spanned by a set S. Okay, now we have a theorem. Let me state it, then I'll prove it. Theorem 3. The subspace spanned by a non-empty subset S of a vector space V is a set of all linear combinations of vectors in S. Okay, so let me explain what it means by all linear combinations before starting the proof. Say we have n vectors in this set S. Okay, so I take linear combination, a given linear combination of these vectors in S. Okay, C1 U1 plus C2 U2 plus all the way up to Cn Un. Okay, now we keep varying these Ci's. Okay, Ci's are in F. Okay, so now we consider these coefficients of this linear combination to be variable. So by varying these coefficients, we get different linear combinations. Okay, so we have a collection of linear combinations. So by the set of all linear combinations, we mean this collection, where the coefficients of linear combinations are variables in F. All right, let's see how we prove theorem 3. Proof: let W be the subspace spanned by S. Okay, then H, so it's useful to have this picture. S is a collection of vectors from the vector space V. Okay, so we have W to be the subspace spanned by S, okay, which is the smallest subspace of V that contains S. Okay, then each linear combination vector U, which is C1 U1 plus C2 U2 plus all the way up to Cn Un of the vectors U1 U2 all the way up to Un in S is clearly in W. Okay. Why? Because W is a subspace, right? So, well, W be the subspace spanning, W be the subspace spanned by this set S. So each of these vectors belong to W, Un belong to W. Okay, now by theorem 1, yes, I think it's no, by theorem 1. By theorem 1, then we see that this linear combination is also in W. Okay, good. Okay, now thus W contains, so thus W contains the set L of all linear combinations of vectors in S. Okay, so this is one important thing. W contains L. On the other hand, S, the set, is contained in L. Okay, L is the collection of all linear combinations, and the set S itself is contained in L, and hence, since S is contained in L, this set L is non-empty, right? Let V and W belong to L, right? Meaning that V and W are two linear combinations of those vectors in S. Okay, and since V and W are linear combinations, there exist these vectors Okay, all right. So here is the important thing. We had this picture of S being the set okay being the set S equal to u1 u2 un, but it may not be the case in general. So to simplify things, we have this picture in the back of our mind, but S can be an infinite set. Okay, all right, so this is where we have come to the general picture where where we take the situation that S can be infinite as well. All right, so this may not be the case in general, so we have to prove the result for the most general case. S is just a set of the vector space which can be infinite as well. All right, so since V and W are linear combinations, okay, and whenever we have a linear combination, we have a finite linear combination. There cannot be an infinite linear combination. So we can talk about a linear combination of n vectors from an infinite set. We cannot have an infinite linear combination. Always remember that. Whenever we talk about linear combination, it means that so there can be an infinite set, but whenever we are talking about linear combination, we have to pick up finitely many vectors from that infinite set and form a linear combination. That's what's happening here. So since V and W are in this collection, the collection of all linear combinations, to be more precise, the collection of all finite linear combinations. We don't say finite linear combinations because whenever linear combinations are said, it means that it's of course a finite linear combination. Okay, so we don't have to say explicitly that it's a finite linear combination because there exists nothing like infinite linear combination. Okay, so if V and W are elements in L, that means that they are linear combination of finitely many vectors in the set S, which can be infinite as well. Okay, all right, so there exist finitely many vectors in the set S such that V can be written down as alpha 1 u1 alpha 1 u1 plus alpha 2 u2 plus all the way up to alpha n un. Okay, let me number this equation by 12. Okay, and this holds for alpha I belonging to the field. Okay, these alpha i's are in the ground field F, and there exist vectors S1, S2 all the way up to Sm, where m need not be the same as n. Okay, they can be in general different. Okay, so there are m many vectors in the set S, which can be an infinite set as well, such that W can be written down as a linear combination of these m vectors, beta 1, S1, beta 2, S2, all the way up to beta m, Sm. Okay, this is equation number 13 for beta I in the field. Okay, now for each scalar C, CV plus W is nothing but the sum over I from 1 to n C alpha I times UI plus sum over J from 1 to m beta J Sj. This is our equation number 14. Okay, this is how we write Cv plus W. So from 14, one sees that one immediately sees that Cv plus W is an F linear combination. Okay, C alpha I is in F. Also beta J's are in F. Okay, so Cv plus W is an F linear combination of the n plus m vectors u1, u2 all the way up to un, s1, s2 all the way up to sm in the set S. Okay. All right. So we picked up two vectors which belong to L, the set of all linear combinations, and we have seen that for a given scalar C, Cv plus W is also in L, right? Hence, L is a subspace of the vector space V. That's the first step. We proved that the set of all linear combinations is a vector subspace of the vector space V. Okay, now let me erase everything. Okay, thus we have shown that L is a subspace of V which contains S. We also have shown that the subspace W spanned by S that is the intersection of all subspaces of V that contain S contains L. Okay, so we have seen it earlier that W contains the set L. Okay, and L in turn is a subspace of V containing S. So the smallest subspace W has to be L itself, right? So let me write it here. W contains L and S is contained in L. Okay, so this guy is a subspace of V containing S, we have seen, and W is the intersection of all subspaces of V containing S. Okay, hence W is that L is that smallest subspace, or the intersection of all subspaces containing S. In other words, L is the subspace spanned by S. QED. Okay, all right. So that's enough for this segment. So we'll be back with more results in the next segment. Thank you for attending this second segment of the 5th lecture.